Polymers are chains of repeat units. The way these chains are aligned determines if a material is crystalline or not. The properties of polymers are defined by their crystalline structures and their side groups. A crystalline material is a material with repeating atom arrangement that forms a long-range order. In non-crystalline materials, there is no systematic arrangement of atoms. There are 7 major factors that affect crystallization in polymers: the repeat unit, molecular structure, degree of cross-linking, copolymers, stereoisomers, strength of intermolecular bonds, and the size of side groups. First, we have the repeat unit. A simple repeat unit promotes crystallization because it's easy to pack each little repeat unit into like a spot on the crystal structure. The complex repeat unit inhibits crystallization because it's hard to put, like, it would take up a big space, and then you would have the extra CH3 molecule sticking up off the top, and it's hard to place another one on there in a nice grid. Then we have molecular structure. With linear molecular structure, it promotes crystallization because it's easy to pack them all in a line on top of each other in a grid. Branching molecular structure inhibits crystallization because when you put one here, you'd have branches coming out, and you can't fit another one nicely up against it because it'd be poked by the branches. Next, we have degree of cross-linking. So this plane and this plane are situated like this, and they need to line up. They're offset from each other. But the amount of cross-links between them makes it very hard for them to move and line up. But with light cross-linking, there are fewer cross-links holding them from lining up. So light cross-linking promotes crystallization, and heavy cross-linking inhibits crystallization.
Alright, so first of all, this R represents any molecule or atom that isn't hydrogen, and these red circles are the carbon atoms with a different molecule attached, while the black circles are a carbon with 2 hydrogens. So our fourth factor for affecting polymer crystallization are copolymers. Alternating promotes crystallization as it allows the chains to line up and form an organized pattern into a crystal. Random inhibits, as there'll be a couple and then chains that line up, and then there'll be a random one that's off, and so the molecules don't line up. Block is the same way. It's pretty much just random with larger chains in between it, but the pattern is still random, that it usually inhibits crystallization. Graft inhibits crystallization for the same reason branching inhibits crystallization. It doesn't allow the 2 chains to line up, as the carbon molecule with the 2 hydrogens attached gets in the way. Our fifth factor for polymer crystallization is stereoisomers. The first one, isostatic, promotes crystallization, as it is an organized pattern that allows for the chains to line up easily. Symbiotic promotes crystallization, but not in the same manner or not to the same degree as isostatic, as it is a pattern, but it's alternating, meaning it's more complex, and so the molecules and chains have to work harder to make sure that they line up properly. Atactic is a random assortment of R molecules or atoms, and it inhibits crystallization because the chains don't line up into an organized pattern, making it crystallization. Our sixth factor for polymer crystallization is the strength of intermolecular bonds between side groups. Strong bonds between these side groups promotes crystallization, as the bonds, like the R bond to the H bond, is strong, making it so that the chains can't move away from each other. They're connected, making it so that they form this organized pattern and they stay there. while the weak bonds inhibit crystallization because the chains will pass each other and not form a bond or form a really, really weak bond, making it easy to break it from the crystalline structure. The seventh factor for polymer crystallization is the size of the side group. Small side groups promote crystallization, where larger ones inhibit, as the outer molecule doesn't allow for the chains to line up as it gets in the way. It should be noted that polymers don't form complete crystal structure as the chains fold around each other, forming amorphous zones. So if this is the chains, they line up, but their ends will be loose and around and wrapped back around in a random assortment to form this amorphous zone in between them. So if this was crystalline zone, it'd be like amorphous zone over here, over here. To recap, we talked about what is a crystalline structure versus a non-crystalline structure, and what factors in polymers promotes crystallization.
Polymer crystallization.